student. We'll continue the chapter surface chemistry, and today we'll do catalysis. So catalyst is a substance, or catalyst is a substance that alters means changes, it increases or decreases, alters the rate of reactions or maybe reactions without being used up, without being consumed in the reaction, and the phenomena is called, and the phenomenon is called catalysis. So you know already this definition we have studied earlier also. So we'll see types of catalysis. The first kind is on the basis of the nature of catalyst. On the basis of the nature of the catalyst, two kinds you have to do in this: positive catalysis, where rate of the reaction increases by adding a catalyst. Example you know very well: nitrogen and hydrogen combining to give ammonia gas, and this reaction takes place in the presence of Fe over molybdenum. Fe is your catalyst and molybdenum is promoter. You have studied this, and rate of the reaction is increased. If you don't take a catalyst, reaction is too slow. Many reactions are there you have studied: sulfur dioxide combining with oxygen, that also you have studied. Contact process, sulfur trioxide is formed. This takes place in the presence of platinum or now replaced by vanadium pentaoxide. So this is positive catalysis. Now the second kind which you have to do, that is a negative catalysis. The meaning you must have already understood. Catalyst which decrease the rate of the reaction. A substance which is added to the reaction and decreases the rate of the reaction, then the phenomena will be negative catalysis. One example very common you have studied last year, this year also, that chloroform in the presence of air forms phosgene, and this phosgene is a poisonous gas, and if we add ethyl alcohol to it, ethyl alcohol is a stopping formation of phosgene, which is a poisonous compound. So this here ethyl alcohol is being used as a negative catalyst, and so phenomena will be negative catalysis. Now the second kind of catalysis, first kind was on the basis of the nature of the catalyst. Now the second kind is on the basis of the nature of the reactant. This is second kind, on the basis of the nature of the reactants. Again, you have to study here two kinds. First kind is homogeneous catalysis. In this case, the reactant is homogeneously mixed up. Reactant homogeneously mixes with catalyst such a way that they form a single phase, that is one phase that is solid, liquid or gas. When your reactant as well as catalyst, both of them are having the physical state exactly the same. So if you take this reaction, nitrogen combining with hydrogen, giving you ammonia, but catalyst you are not taking iron, but you are taking nitric oxide. So this is a gas, these are gas. So these all are gases, and therefore they are forming a homogeneous solution and they are in one phase. So such catalysis is called homogeneous catalysis. Another common example is your ester, you can take, or acid, that is carboxylic acid combining with alcohol in the presence of, this reaction is reversible, in the presence of mineral acid. Normally H2SO4 is taken, and we obtain RCOOR dash water. This R in this reaction you have studied in alcohol, and we obtain this. So reactant, now these all are in the liquid phase. This is liquid, this is already iron liquid, this is liquid, and here these all are gases in the gaseous phase. So this is another example common, quite often asked. And one more example which is quite common, that is hydrolysis of sucrose, C12H22O11, water in the presence of mineral acid, and we obtain one molecule of glucose and one molecule of fructose. These reactions you have studied in the lower classes. Fructose. So all are here also in the liquid phase. All liquid. Solution. And so this is the example of here this liquid you should not write actually aqueous solution. So liquid phase. So we obtain this. So this is homogeneous catalysis, and now I'll tell you the theory of homogeneous catalysis, that is in the syllabus, and theory of homogeneous catalysis. This is also called intermediate compound formation. Intermediate compound formation theory. So, yeah. In this case, what is happening? Homogeneous catalyst forms an unstable intermediate with reactant. One thing, intermediate, unstable intermediate, which has, with what has, this intermediate which has low activation energy. Yesterday I told you about activation energy. Activation energy is the minimum amount of energy required for a reaction to take place. So low activation energy, which has low, what has low activation energy? Intermediate has low activation energy. So because of this low activation energy, zone that is forming and decomposing. So this intermediate which is formed, that is called this intermediate decomposes, either decomposes or reacts with other reactants, decomposes to the end product. Either it decomposes to the end product or this reacts with other reactant and then they get decomposed and then forming your end product. So this you can understand this way if I explain this to you. It is more based on chemical kinetics. If I show you a reaction graph, suppose you have A and B as two reacting and they are combining and giving you C and D as products. So these are reactants and these are products. Here I have taken in the atomic form, but if they are in the molecular forms, it will be A2 and B2. A is bonded with A and B is bonded with D. For the convenience of the reaction, in the atomic form I have shown. So, if here I take reaction system and here versus energy. So, these reactants have got certain amount of energy before the reaction, and when their energy is raised to certain temperature such a way that this A molecule bonded with A, that this bond gets stretched and B bond also gets stretched, and when they are in contact they are establishing another weak bond between dissimilar atoms. So none of this bond is forming, but they all are in a close vicinity. So this species which is formed, that is formed when they have attained some amount of the minimum energy that could stretch their pre-existing bond, and at the same time a new bond between different atom could also be established temporarily. So this state which is formed, that is called intermediate, and the energy which is required by these reactants to form this, that is called your activation energy, uphill task. So here, if these reactants are here A plus B, they have gained energy so much, and suppose when they have reached to this height, and then this energy they have attained here, and let this energy be activation energy. And then what will happen here, the activated complex is formed. Activated complex is formed. And then what will happen, once they have attained this energy, then this will break, this will decompose, and this bond will become permanent, and we will have a new species form, AB, which I have taken as C plus D. So we will have the products form. So this is here, this will be converted. Here you can write AB also, but this is just presentation. So these are the products which will be formed. So the products will be formed, then as much amount of energy they have absorbed, they will release. So that is part of kinetics I am not covering here. So we have got the product. So this much is the energy is required. Now what happens, this is activation minimal energy, they needed AB to be converted into CD. And when they attain so much energy, the activated complex is formed. When we use a catalyst along with this, then they need energy, but activation energy is lowered. We know they don't need now so much of activation energy, now activation energy is low because of the catalyst. So activated complex is formed here, and energy is now, activation energy is only so much. So this is if your EA dash, so EA dash is less than EA. So this is without, this is with catalyst, when we have taken catalyst, and this is without catalyst. So this is what here, this is the theory of intermediate. So what this catalyst is doing, catalyst is providing a new path which has low activation energy, and that's why what is happening, rate of the reaction is increased. In lesser time reaction is getting over, and the product is formed. When the product is formed, here this is happening, taking place on the surface of the catalyst, and once the product is formed, the catalyst is regenerated. Catalyst is only lowering its activation energy and is providing a center for the reaction, site for the reaction. Reaction is taking place, catalyst will be out, and reactants will be turned into the product. And so that is your homogeneous catalysis. Now heterogeneous catalysis. The second catalysis is a heterogeneous. Heterogeneous catalysis, and in this case reactants are not homogeneously mixed with the catalyst. So there is no one phase. There may be two phases or more than two phases. Examples you have seen already: nitrogen, which is a gas, hydrogen, which is a gas, both are reactant, taking over iron, which is the catalyst, solid. So this is gas, but this is solid, and we are obtaining gas. So catalyst in a different physical state. So on the basis of the nature of the reactant or the physical state of the reactant. So here that is your this is reactant is gas, catalyst is solid. So it is also called, since it is taking solid catalyst, so it is taking place on the surface. So therefore it is also called surface catalysis. Also called surface catalysis. Okay. Now we'll do the theory. Theory of heterogeneous catalysis. Theory of heterogeneous catalysis, also called adsorption theory. Adsorption theory. So we'll understand this. This takes place in several steps. The first step is step 1. Chemisorption. Chemical adsorption. You have studied yesterday in the previous class. Chemisorption. Chemical adsorption. Chemisorption of reactants on the surface of catalyst. The catalyst is solid state and reactant is in the gaseous state. We have studied in the previous class. So in this, what is happening? That is the catalyst provides active sites on its surface by free valencies. Free valencies will be there of the surface metal. This is solid iron is an example. And because of this active site, because of the free valency, free electrons, what will happen? Reactants chemically combine. Means what? They are establishing a bond. Chemically combined with the free valencies of catalyst and form valencies and free valency here. This much is taking place. So when they are forming a bond, valence bond on the surface, that phenomena is called chemisorption. So in the first step, the chemisorption is taking place of the reactant on the surface of the catalyst, where catalysts play the major role. They are providing free valency, that will be their active site. Now, the next step, step 2. Is step 2. After chemoabsorption, so chemisorbed reactants will combine together to form an unstable complex on the surface of the catalyst. Unstable means it will decompose itself. So that will decompose itself to produce the end product, and the catalyst will be free regenerated. So once this unstable complex is formed on the surface, then next step takes place, step 3, that is called desorption. Desorption of products. The products which are formed, they are given out and the catalyst is reformed. So this is the theory of heterogeneous catalysis. And now the characteristic of catalyst. Characteristic of a catalyst. Characteristic of a catalyst. Only 3 characteristics you have to study. First is specificity. Also you can call it selectivity, and surface area, activity, and surface area. Specificity or selectivity, same more or less. Specificity means for a particular reaction. This term is for enzymatic reaction, and this is for chemical reaction. So you know that a biology student must be knowing. In class 10 you must have studied there are some enzymes. They only act in like a catalyst, by name the biocatalyst, in a one particular reaction, like your carbohydrate in the mouth, that is glucose, can be digested by only salivary amylase, not by any other enzyme. So one particular enzyme will be acting upon a particular chemical compound. So enzymatic activity, that catalysis is specific for a reaction. So that is what is a specific catalyst. So one kind of enzyme cannot react with all other chemical compounds in the same way. Similarly, selectivity, if you see the example, you have studied the reaction ethyl alcohol. This is combining with or when it is heated in the presence of copper at 300 degrees Celsius, then it is forming acetaldehyde, CH3CH2, and the hydrogen gas is out. And when this ethyl alcohol you take and you heat at the same temperature, but in the presence of alumina, you get CH2 double bond, CH2 and water. So here acetaldehyde and water. So this is selectivity. When in a different catalyst, same conditions, same reactant, but products are different. So for chemical reaction, when we use it is selectivity, and for bioreaction, enzymatic reaction, then it is specificity. So selective nature, catalysts they have. Activity, that is they are altering the rate of reaction, you have seen already. They increase mostly rate of the reaction, but in some cases they may decrease also the rate of reaction. Example you can read from the book. Surface area also we have seen in the previous class. More will be the surface area, more faster, active will be the reaction. And so here it finishes your catalysis. My next topic will be collateral state. So that we'll do in the next class. So till then, bye.